In this example, we want to compute the expected value of a particular random variable, but what you might notice is that the expected value formula would be the same as the mean formula. So in other words, we can kind of interpret it the same way, that the expected value of a particular random variable is the same as the mean value of that. And one way we can also think of it is it kind of tells us if we were to maybe perform our experiment many times, what would be the most common outcome to expect? In other words, what would be the most likely outcome to occur? And one way we can use it is, for instance, in this example, when we're calculating the expected value, or the perhaps we can interpret it as the amount of money we might expect to win playing a casino game. So there's a game in Vegas where you pay $1 to play with the possibility to win either $5 or $10, meaning you receive a net payout of $4 or $9. The probability of a payout of $4 is 0.3, and the probability of a payout of $9 is 0.1. Find the expected value for this game. Okay. So let's break this down. We have two possible ways of winning. We have a 0.3 probability of winning $4. We have a 0.1 probability of winning $9. But because it costs us $1 to play, whenever we lose, which will occur, well, let's see, if we have a 0.3 probability of winning $4, a 0.1 probability of winning $9, well then the rest of it has to add to 1. So the probability that we would lose would be somewhere around 0.6. So in the case when we lose, we have a 0.6 probability that we'll lose that $1. But in the cases where we win, we have a 0.3 probability of winning $4, and we have a 0.1 probability of winning $9. And so that 0.6 that we got there was to make sure that these values here have to sum to 1. You can check these sum to 1. So what we have in this table is essentially our probability distribution, where the amount that we're going to win is given as a random variable x. So we could win negative $1, meaning we really lost $1. And so the expected value here would be summing up all these x's times p of x. So like the first x would be negative 1 times the probability of that occurring, which would be 0.6. And then the next x times p of x would be 4 times 0.3. And the next x times p of x would be 9 times 0.1. And when we compute all that, we get something, so that would be negative 0.6 plus 1.2 plus 0.9 gives me about 1.5. So the way we would interpret this is that after we play this game many times, we expect to, on average, to win about $1.50 every time we play the game. It's actually not a bad game. So on average, you'd expect to win $1.50.